Hi, in this video I'm gonna talk about characters and some of their properties. So let's start with the definition. Let's take a group G and a field K. So now we're gonna define what a character is. So a character, let's say from G to K, is a group homomorphism chi from G into the multiplicative group of K. So this is the kind of number theoretic definition. There exists also a representation theoretic one, which is related but not the same. Okay, so now we have our definition. Maybe first a few remarks. So some authors define characters just over the complex numbers. So where the homomorphism goes to C star. But for us, we're a little more general. We take any field. And maybe another remark, there exists a trivial character which just sends everything to 1, because 1 is the multiplicative unit in K. But this is not the most interesting one. Okay, so let's start with the following lemma, namely the orthogonality relations for characters. Or let's say one kind of orthogonality relations. Later we'll see other ones. Okay, so now, and also in the following, we will always take a finite group. And K, any field. Okay, and now we take a character. So let chi be a character such that there exists some G0 in G with chi of G0 not equal to 1. So this just says let chi be a non-trivial character. We could also take the one which sends everything to 1, but then the statement is not interesting. So what is the claim? Then the sum of chi of G, where we sum over all elements in the group, is equal to 0. Later we will see a similar claim, but instead of summing over the elements in the group, we take a fixed element in the group and sum over the characters. Okay, so let's start with the proof. So, well, let's start simple with, let's have a look at the sum. Okay, we can write the sum differently. Namely, we can write the sum as a sum over G in G, and then we can sum instead over chi of G times G0. So this is just reordering the elements in the group. But it's a bijection because we have this fixed element G0, and so chi is a character, so we get sum G and G, chi of G, chi of G naught. Okay, but we're in a field, so we can pull out the chi of G naught, and we have the same sum we had before. So now we are almost done. We subtract 1 from the other, and after subtracting 1 from the other, since everything was an equality, we get 0. But this thing here is not equal to 1, so therefore the latter sum has to be 0, and we have proven our lemma. Okay, so far so good. So the next goal would be to prove the same thing, but summing over the characters. So let's first of all have a closer look at characters. So let's state the following lemma. So let's again take G be a finite group, and again K a field, and then the claim is the set which we denote by G hat, which is just the set of characters from G to K. So chi is a character. This set forms a group. Okay, let's prove it. So first we have to define what is our group operation. So let's take 2 characters. Oh, here there's a star missing. Have I been missing it somewhere else? Hope not. No. Good. Okay, so we have 2 characters, and we define the group operation as follows, namely just by pointwise multiplication. So this is just defined to be chi 1 of G times chi 2 of G. Okay, so now we have our operation. So first of all, maybe note that associativity follows from the associativity in the field. So the units in the field form a group, so that's fine. And so I already spoke before of the trivial character, so this we define just to be 1 for all elements in the group, and it's easy to check that this is the neutral element. Maybe as another remark, also I should have maybe said this before, but so here this is really, it's easy to check, but this is actually, so multiplication is well defined, so the product of 2 characters is again a character. So this means we have to plug in 2 elements, so the product of 2 elements from G, and then we get again the product of, so what I want to say, chi 1 times chi 2 is again a homomorphism. Okay, and now lastly, for chi in the group of characters. So we have to show it's a group, but in a set of characters, we define the inverse as follows, namely chi inverse of G is equal to chi of G inverse. And it's easy to check that this is really defines an inverse. Okay, nice. So we have our group. Maybe a small remark. So if we would have taken the complex numbers as our field, then actually chi inverse would be the complex conjugate of chi. But that's just as a remark. You can prove that as an exercise. There's a small trick you need, but I hope you can figure it out. Okay, so now we're in a place to prove the other kind of orthogonality relations. So we had these ones. Now let's prove by summing over the elements in the group of characters. So again, we call it orthogonality relations. And so again, G is a finite group. K, a field. And well, we have to make one more assumption. So assume that the group of characters is not just given by the trivial character, and let's take an element. So also G should not be just the trivial group. So let's take an element from the group, which is not the neutral element. And the claim is then the sum over the characters of chi of G is equal to 0. Okay, so let's prove this. So we can actually, let me think, we need a little bit more. So actually we need, let me rewrite the statement. And chi naught of G not equal to 1. So we need a little bit more. So this already implies that the group of characters is larger than 1. So we can kind of ignore this. And then we get this statement. So this is automatically true, for instance, if we work over the complex numbers, but I wanted to state it more general. So we have to be a bit careful with how we state it. Okay, so let's prove it. Let's take a character, sum over it, Okay, but now we know that actually the characters form a group. So this is also the sum over chi in the group of characters. And then we could do chi times, how did I call it? Chi naught of g. But so this is now just by definition and by pulling it out from the sum, chi naught of g, sum over the characters, chi of g. And similarly as before, we get 1 minus chi naught of g. This thing here again is not equal, it's not equal to 0. Did I before write 1? I think should be a 0. Not equal to 0. And sum over the characters and chi of g, and again the statement follows. Okay, that's it for today. Thanks everyone. So in the next video we're gonna probably use it for some results on equidistribution. So have a good day. Bye.